continual improvement. We talked about the fact that we have to do some planning. With the advent of our technologies and the availability of digital engineering, we can actually do a lot of the planning and the engineering in a virtual environment. So this part has allowed us to be a bit more front-end heavy with respect to these types of aspects, okay? Once we have that, we then have to relay this information to site. This was a part of essentially your lab, right? So for instance, what we did with the disto, that's an example of that, on how we would be able to minimize as much as possible the miscommunication between the information that we have in the plan and the digital model to the reality, right? Once we have that, we still need an extra check there. And this extra check could come from optical instruments, it could come from IoT sensors, whatever it is. Preferably it's going to be some sort of sensor system that gives us some frequent data that we collect. Based on the data that we collect, we go ahead and compare it with our plan, see if it matches. This could be in terms of progress, this could be in terms of quality, or this could just be in terms of our analytics. We're going to be collecting this data, hopefully to have some historical data that we're going to be using for other aspects later on as well, right? So let's say at that particular time we make a decision, we can actually record that decision. Once we have that, we then, dependent upon how these are changing or it's not, let's say, complying with our plan, then we can make some sort of decisions. Once we make the decision, we have to go back and actually revise our plan for the remainder or for what we have there. And we talked about the fact that if we identify these earlier on, what is going to happen? We're going to have higher chances of us being able to prevent these before it needs rework. And what is the problem with rework? Rework is a basic definition of waste. It's a waste in terms of our time that we're going to be having, as well as the costs associated with it, right? So that's the basic parts of it. And these are simplifying it, obviously, in a very siloed or a very iterative way, but we can distinguish them somehow by means of digital engineering, the constructive facility, our performance assessment, and then this essentially is going to go on a cycle, which is the equivalent of the total quality management in industrial projects. And that is what we call the Deming cycle. So it's called plan, do, check, act. And this is what we essentially do in these construction projects as well, okay? And this is essentially tying with the field information modeling side of it, which is we have a lot of information with the, let's say, building information modeling or the front end side of it. We also have to have an idea about how we're modeling this information on construction projects or as basically this construction is going to progress, right? And that's the whole idea of that. The modeling of that information from the data collection side of it, the decisions that we make from that, and everything else for us to be able to take some sort of data and information and make better decisions. That's essentially what we're doing, and that's what we're practicing here, okay? We can categorize it or summarize it into three different parts of information that we need in order to make better decisions based on the information that we get from the site. One of it is with respect to what type of information about the plan do we have available, okay? So if we have many dimensions of our BIM available to us, we would be able to use that information as our baseline so that we can compare it with existing information that we extract. So that simplifies our process a bit, right? So I give an example. If we have, let's say, a 3D model that is completely segregated, as an example, every element of this model, we know what it belongs to, what, let's say, characteristics and properties it have, and using that, we would be able to use that as a baseline information. If we have that baseline information, what do? We collect information from site, and then we compare it with that baseline information. If we have an accurate baseline information, we would be able to accurately simplify whatever data we collect, summarize it into the information that we want from the baseline, and then compare them together, right? But if we don't have accurate baseline, we would have no opportunity to be able to compare these together, right? So I give an example of if we have no construction error. So if we have no construction error and we collect a point cloud and we have a good graphical 3D BIM or 4D BIM here. The problem is quite simple. We have no construction error, yeah, and we have all of the elements, and we have it in 3D or 4D. First thing that we want to do is to, let's say, identify for every element, very simply, just register these two together. If the coordinate systems are the same, in terms of the distances from the point to every surface, we would be able to see how far they lie, okay? Using that, simply, we can see if these particular points are going to be within the tolerances that we expect are point cloud measurement errors. So if we don't have significant construction errors, we have construction errors within tolerances or within reasonable, let's say, deviations, we would be able to easily identify that. So that's not a complex problem to solve. I give an example of this so that you can understand with respect to the information that we have from the baseline, as well as the basic characteristics of our construction, the complexity of how well we're going to be processing this information and analyzing it and using it to make different decisions also changes, right? So this has a simple solution. If you have a construction project where the baseline information is not going to be defined well, and you're going to have construction errors, and you're going to be having very, very bad noisy point cloud, then in order to automatically acquire the analytics that you want from construction projects is going to be harder. That's what I'm trying to get at. Okay, so this is an example of if you have some construction errors. So if you have some localized construction errors, and if you just register these two together, you're going to be observing that you're going to be having some elements in terms of its errors. With respect to this, we have to have a better solution to be able to identify these errors and to observe how far are these errors from the actual tolerances. If, again, this is very small, it's not going to be problematic. But that by itself is important for us to define. What is this small? Is it 5 centimeters? Is it 4 centimeters? Is it 10 centimeters? What is it? Okay. For that, that means whatever method that we're going to be devised in order to process this needs to be immune and robust to larger errors, right? That by itself means that the method needs to be a bit more complex than just seeing the distance between every point and the surface and then making a judgment based on that, right? Okay. What if you have incomplete graphical information? Well, if you have incomplete graphical or non-graphical information, because whatever we have is with respect to the baseline, we collect data and we make decisions and judgments based on how well we're doing. If we don't have complete graphical information, well, we have to go to the non-graphical information. I'll give an example. For instance, in many of these residential buildings, some of these, let's say, mechanical subcontractors or different types of subcontract work, they might not have, let's say, 3D models or 4D models or models in general that have any type of intelligence. They might have some blueprints that requires additional processing to extract that information. For that, you can use some natural language processing from the technical specifications of the particular project and then extract that baseline information. Okay? This is where I'm saying that the complexity of the problem arises and the information modeling arises as the incompleteness in 3 important aspects also change. One of them is going to be the design or the planned information. The other one is whether we have construction errors or not. And the third one is the instrument itself that we're using for a collection of data. In this case, we're going to be given the example of point clouds because that's what we're going to be working a bit more and it's a bit more tangible. But there are other aspects as well, other types of information that you can collect as well, right? Okay, in this case, we get the relevant information, for instance, what type of pipes we have. And then once we collect this from this, then the problem here is that we do not know more or less where the locations of these pipes are. This is what I'm saying when we don't have graphical information. Let's say I know that I have some columns that I need to extract from this room and I collect the point cloud, but I don't know where I'm going to be looking for columns. That's going to be a much harder problem to solve than if I know more or less that there's going to be a column over there. right? That's where you're going to be seeing that if you have graphical information that is going to be in 3D, the processing of it becomes a bit simplified, right? And in this case, you would have to do some just general, in this case, it's pipes, so it's going to be cylinder fitting. If it's columns that are going to be rectangular, it's going to be plane fitting and plane extraction from completely unorganized point clouds, right? So it's going to be a bit more challenging. So this is if you have some incompleteness. So I give some basic examples here. And this is essentially a Stacy complexity matrix. I give it in 3 different categories. One is the errors in planning and design. That's if you don't have complete information, or you don't have, let's say, 3D information, or you don't have 2D information. And dependent upon how well your technology is going to be, you are going to be having some difficulties in identifying your baseline information. If you don't have good baseline information, how are you going to be identifying how well you are doing? Okay, so knowing your baseline information by itself is a problem, and it's going to contribute to the complexity of your point cloud processing or of your field information modeling. The second one is the instrument. In this case, I say point cloud instrument. So you guys have certainly played around with your phones, right? Even from phone to phone, you're going to be having point clouds that have different, let's say, errors associated with it, right? If you're using laser scanners, it's going to be different. Each and every one of it is going to cause some complexities. If you have a laser scanner that is terrestrial, okay, that's going to be much higher in accuracy than even a mobile laser scanner. If you're using an iPhone versus a very high resolution camera, that's going to cause differences in the accuracy, right? That by itself is going to contribute to the complexity of how well you're going to extract information from the point cloud itself, okay? And the third one is construction errors. And as an example of this is, imagine if this is a column here, and you even have 3D BIM or whatever digital model that you have that is quite accurate. And you're expecting the model through the model to actually be here, but it's here. If you just think about, I'm going to look at all of the points that are within 5 centimeters of this, but this is 20, 30 centimeters away. You are not going to be able to identify this, right? So how do you proceed? And that's the whole point. If you have considerable construction errors or mismatches between the plan and the actual as-built that you get, the complexity of the problem that you're trying to solve actually increases. And that's what I'm trying to show here. And I put it into 3 levels. The first level is the simple problem where you can actually solve it by a simple distance matching. Okay, so you have the point cloud that is relatively complete. You have the model that is complete as well. And then you just have a distance to model basis. Using that, you would be able to identify what every point is and what every point belongs to what element of the model. The second level is a bit more complex, and this is the case of prefabricated elements. So we know that the element itself, the size of the element, is not going to change. So we know that we're looking for a column that has this size. Okay, we're not looking for a column, or if it is, you can still parametrically identify that, or let's say scale it somehow, right? That's the second level that we have, and at least we have a 2D model of that. And then the third level is that we kind of go free fall, meaning that the element itself also can change in size, and it's not supposed to be in the proper location either. Okay? These are how basically I've done that, and every one of these is a bit more complex problem. And that's where I also devised this, which I showed you before, which is an AI-based method that superimposes the model onto the point cloud, right? And I only deal with it in 2D. And I say that I'm going to give it a very exaggerated orientation and translation And if a method that is going to be recovering this is good, is going to be immune to large amounts of transformations and rotations, okay? And that's what we're trying to devise here. So we do an AI-based method and we get all of those information from there. If we have this ability to do this, or our method is robust to that, it could solve particular types of problems. In this case, it solves the level 2 problem. So this is not there to solve the level 3 problem, okay? And aspects of level 3 problem has been solved, and some aspects, hopefully you guys would solve it later on when if you get interested in this and you basically start up your own companies or you're in your organizations and you go forward with it. So we go into how are we going to be collecting some visual data and information, starting with a single camera. So you have a single camera and you have the construction project. Let's say we want to extract whether these beams on top is going to have some correspondences here. Then we have to superimpose these together, do some image processing, and then extract and identify whether those pixels actually belong to a beam or not, and then from that make a judgment and decision there. And the goal here is to make it as automatically as possible. Again, it's not simple in absolutely every problem, but in some problems where we have a bit of a lower, let's say, amount of construction error, we have that opportunity, okay? The other one is if we have some point clouds, the point clouds, you have to superimpose these together and find whether you're behind or ahead of schedule.